US Physics Olympiad year 2018 USAPHO. Problem A3. A vacuum system consists of a chamber of volume V connected to a vacuum pump that is a cylinder with a piston that moves left and right. The minimum volume in the pump cylinder is V0 and the maximum volume in the cylinder is V0 plus delta V. You should assume that delta V much less than V. The cylinder has two valves. Inlet valve opens when the pressure inside the cylinder is lower than the pressure in the chamber, but closes when the piston moves to the right. The outlet valve opens when the pressure inside the cylinder is greater than atmospheric pressure PA and closes when the piston moves to the left. A motor drives the piston to move back and forth. The piston moves at such a rate that heat is not conducted in or out of the gas contained in the cylinder during the pumping cycle. One complete cycle takes time delta t. You should assume that delta t is a very small quantity, but delta v over delta t equal R is finite. The gas in the chamber is ideal monatomic and remains at a fixed temperature of TA. Start with the assumption that V0 equals 0 and there are no leaks in the system. Questions. Question A. At time t equals 0, the pressure inside the chamber is PA. Find an equation for the pressure at later time t. Question B. Find the expression for the temperature of the gas as it is emitted from the pump cylinder into the atmosphere. Your answer may depend on time. For the remainder of this problem, 0 less than V0 less than dV and much less than V. Question C. Find an expression for the minimum possible pressure in the chamber P minimum. Solution for the problem. Question A. At t equals 0, the pressure inside the chamber is PA. Find an equation for the pressure at a later time t. Solution. During each cycle, the system sucks gas out of the chamber and pushes it into the atmosphere. Since V0 equals 0, the inlet valve opens the moment the piston starts moving to the left. When the piston is all the way to the left, a fraction of delta V over V plus delta V of the gas is in the cylinder. As the piston moves to the right, all of the gas is pushed out, so after a single cycle we have P final equal P initial multiplied by V over V plus delta V. And in general, P is a function of t equal PA multiplied by V over V plus delta V in power of t over delta t. While this is technically correct, it can be simplified significantly. P as a function of t in form of this one or this one, where x equal delta v over v, which is much less than 1. Then, using the definition for exponent as such limit, we have p as a function of t equal pa multiplied by exponent in power of negative rt over v. That was a solution for question A. Question B. Find an expression for the temperature of the gas as it is emitted from the pump cylinder into the atmosphere. The answer may depend on time. Solution. When the piston is all the way to the left, the pressure is Pt and the temperature is Ta. As the piston moves to the right, the gas is adiabatically compressed until its pressure reaches Pa, and the outlet valve opens. Since PV power gamma is constant during adiabatical process and the PV over T is constant by the ideal gas law, we have T out is equal to this expression, and because for monatomic gas we have gamma equal 5 over 3, and question answer, we have this answer for question B, that T out equal Ta multiplied by exponent power 2RT over 5V. So that was a solution for question B. Question C. Find an expression for the minimum possible pressure in the chamber, P minimum. Answer. Since V0 greater than 0, the inlet valve will not open immediately when the piston begins moving to the left. Instead, it will open once the pressure in the cylinder equals the pressure in the chamber. Since the expansion of the cylinder is adiabatic, we have PV power gamma is a constant, so P minimum equal PA multiplied by this expression or this formula. That was answer for question C, and that was answer for all three questions for problem A3.